All right, let's go ahead and get started today. Can you all hear me okay? Thumbs up?
Yep.
Awesome. Cool. All right, so today we're going to really get into the details of some of the compiler passes. We'll see how many of them we get through. We'll get through a bunch today, and then whatever ones we don't get to today, we'll go over on Thursday. And so this is really should be giving you hints, pretty strong hints about what each pass should do, and some hints about how to structure your code for it. That being said, I don't want to give it completely away and leave room for some fun on your end of figuring out what to do. But feel free to ask questions. Any questions, totally fine. I'll be happy to answer it. Actually, before we dive into that, though, let's spend a minute or two talking about collaboration in terms of how you all are going to collaborate with each other. It could very well be that you all are on top of this and already know how you want to collaborate with each other, but if not, maybe it's worth talking about. Have any of you already started collaborating, and how are you managing that in sort of the current COVID-19 situation?
I know my group is using Discord. It has a really nice, just communication and screen sharing functionality that we like.
Mm-hmm. Cool. Has screen sharing, does it have video too? Yeah. Cool. Yeah, Discord, I've just started using it as well in the last few months for a collaboration with people at Google. And I guess it came out of the game programmer sort of community. That's where it originated. At least that's what I hear. But yeah. Cool. Yeah, so that sounds like a good option. Is anyone using other tools besides Discord?
My group is like messaging each other on Slack. We have like a 3-person group message on there.
Mm-hmm. Cool. Yeah. Slack, and then if you're already on got your stuff on GitHub, then that's sort of a decent way to look at each other's code as well, as long as you're pushing fairly often. Cool. So Slack, yeah, that's good. Of course, there's Zoom. I think you all can use Zoom as well to talk to each other. So that's an option. Okay. Any other technology choices out there? I suppose even in person's okay as long as you're physically distanced, but oftentimes that means outside, and that may actually be more difficult than being on a Zoom or Discord or something like that, and doing screen sharing. So, yep. All right. Okay. Good. So let's move on and start talking about the passes. I'm going to share my screen. Oops, having some connectivity issues, but there we go. Hopefully this cord is reliable enough. If not, I'll switch to a different cable. All right, so first let's just kind of look at a high-level view of the compiler passes. Okay, so we've got this language R1 that we're compiling. And the first thing we're going to do is uniquify that. And the output of that is also in the R1 language. I'll put a little apostrophe after it because there's something that's going to be true of the output that's not true of the input, right? The whole point of uniquify is to make sure that every variable in the program is different. Okay, so the output of uniquify will have that property, whereas the input will not. So that's why sort of a little asterisk there. Okay, so uniquify just basically changes all the variable names, making sure they're unique. Then the next one is remove complex opera star. Okay, and that also goes to R1. I'll give it a double prime here. I'm not going to actually give like different grammars for these different versions of R1. Okay, but we'll just sort of describe the differences. So remove complex opera star. That's the pass that's going to make sure that the sub-expressions of an operator like plus are atomic. That is, they're just a variable or a number. Okay, and this is helping us get closer to, the format that x86 instructions are going to want to see things in. Okay, so that's remove complex opera star. We're still in R1. We're just basically adding a lot more let bindings. Okay, a lot of temporary variables with let bindings. Okay, then the next pass is a pretty important one, and it takes us to a new intermediate language called C0, and this is explicate control. Oops. Okay, and C0 is named that because it's a little bit like C in some ways. I mean, it's different in others, but it's like C in that it has expressions and statements. So it has a couple different kinds of syntactic categories. It has, you can assign to a variable multiple times in an assignment statement. So you've got that instead of let bindings. But the main point of this pass of explicate control is to go from a world where your control flow is this depth first search of your program into a world where your control is really explicit in the syntax. So if you're just going sequentially through the program from one statement to the next, okay? And then as we add more complicated forms of control flow, like branching, again, you'll have explicit branching with jumps in C0, whereas, in the R1 or R2 languages, that kind of jumping will be more like structured control flow, like if expressions and things like that. All right, so that's explicate control, gets us down to C0. And then from C0, we'll go down to x86 with a little star there. So that's pseudo x86, and this is select instructions. And so select instructions is going to do things like take, an assignment statement and turn it into like a move instruction. Or maybe you've got an assignment with an addition on the right-hand side, that'll turn into an add queue, okay? So you're generating instructions, but the reason why it's called pseudo x86 is that we still have variables kicking around, and we still have an unbounded number of variables. So we don't have we're not using registers yet or stack locations, and we're not necessarily obeying all the rules about what instructions have to look like. Okay, so then the next pass is assign homes. Okay, and so that's going to replace variables. Now, in this first assignment, it's going to replace variables with stack locations. Okay, and this is going to be fairly straightforward because we can use as many stack locations as we want. We can just use one per variable. It's straightforward. Okay, and after this assignment's finished, next time for the next chapter, then we'll get into register allocation. And then the reason why we call it assign homes, the home is sort of generic, meaning like it could be a register, it could be a stack location. Okay. So that pass will get more interesting later on. Okay, then the next pass takes us to x86 abstract syntax trees, and that's patch instructions. Okay, So this pass is going to deal with making sure that that we actually adhere to all the rules about what instructions have to look like. For example, you can't have too many memory references, stack references in the same instruction. You can only have one, not two. So we'll fix up a few instructions in that pass, and then the final step goes to x86 as text, and that's just the print x86 pass. Okay. So that's it. That's the entire compiler. So if you haven't started working on it already, I definitely encourage you to get hopping. This is not a one night kind of assignment, okay? Maybe 2 or 3 nights or more, depending. So definitely get on it, and then we'll be available for office hours like tomorrow, Thursday, and so on. The office hours are posted on the course webpage. I'm a little, the deadline I've got on the web page is Monday. I know life is complicated these days, and if that looks like it's difficult for many of you, then we'll think about pushing that back. But just definitely get started on the assignment. If you feel extreme anxiety about it, please talk to me, and I'll try to be understanding about that. Okay, any questions about sort of just this overall flow of the compiler? And I've managed to open up the chat window so I can see if you type in there as well this time. Okay. All right, so let's dive into the individual passes. Okay, starting with Uniquify. Oops. Okay. So I like to show examples to sort of give you an idea for what passes should do. Right, so again, this one is supposed to replace variables with variables that have unique names. So for example, let's say you just started out with a little program like this. X is 32, let y be 10, plus xy. All right, so if that's your input program, then your output program, it would be reasonable to have it look like the following. And the idea is that maybe what you're doing is applying GenSim or something. Right, it's that's short for generate symbol. That's a built-in function in Racket, even in old Scheme, for generating a new symbol. And it takes an argument, right? And the argument can be like the old symbol that you want sort of like a new version of, and then it include the old symbol as part of the new name. It won't look quite as nice as what I'm using here with this dot notation, but it'll definitely be unique. So here I've got, you can imagine using there's a counter or something going on. Okay, and of course I have to also change the uses of the variables to match the new names that I've given them. Okay, so X turned into X1, Y turned into Y2, let's say. Okay, all right, so that was a simple example. Let's do a slightly more interesting one. Right, so one of the main points of Uniquify is to deal with shadowing of variables. So let's do this. We've got this example again. So we have x gets 22, and then plus, let x be 10, and x, and then x again. Okay, so we've got two different definitions of x, and then we've got a couple different uses of x. And when we do our renaming, we need to do it in a smart way that matches up the appropriate ones according to the way the shadowing works, you know, the way you search up the scope. Okay, so here we're going to get let's call this x1 plus let, right? So now this is a different x, so it's x2, it's 10. And then this inner x here, of course, that's going to be referring to x2, okay, because that's the closest one. And the x1 would be overshadowed by the x2, okay? And then down here, there's only one x in scope, it's the x1. And that's that, okay? Any questions about that example? Okay, so now, as will be the advice with just about every pass, you'll want to implement this with a recursive function, okay? So there'll be like, the uniquify will be like the name of the function for the whole program, but then you'll have something like uniquify dash exp will be the recursive function that processes expressions. Okay, so you're writing that recursive function. How are you going to deal with the variable renaming? What's going to be your strategy? Let's go ahead and brainstorm some strategies for dealing with the variable renaming. Any thoughts?
We could try to do like structural recursion and keep like an environment that we have. So
Yeah, so those are both good things. So structural recursion, right? And that advice is going to be applicable to pretty much every pass, okay? But then the second thought there was use an environment. And could you say a little bit more about environ? Oh, I can't spell. Can you say a little bit more about what you're thinking with the environment?
I'm not quite sure yet, but definitely some sort of list or whatever that has the variable names that you've seen. So
Oftentimes,
supposed to be for?
Sorry, what was that?
Is that what the symbol table is supposed to be for?
Yeah, there's different names for this kind of thing. Environment is sort of a typical name you'll hear in sort of functional programming circles. In more like conventional compiler literature, you'll see symbol table. And symbol, you know, in some circles is a synonym for variable. But the main idea here is that you're going to have a mapping from variables to something else, right? That's typically like let's say you're doing type checking, you'll typically have a mapping from variables to types. Okay, let's say you're writing an interpreter, or you saw the interpreter for R0 a few lectures ago. There we had a mapping from variables to values, okay? So here for uniquify, it's a mapping from variables to the new variables, right? To the to the renamed ones. Okay, so for example, in this program here, by the time we're processing the body of this let binding, okay, we'll have built up a symbol table that says X goes to X2, and then maybe further down the symbol table, it says X goes to X1. Okay, and the symbol table will be like maybe a list of pairs. We call an association list. And you always go from front to back when you're searching through an association list. And so this will cause the right behavior for shadowing. So you'll hit the X goes to X2 first, and then that'll cause you to rename that inner X to X2 as appropriate. Okay. So and as you're processing, like when you get to a let, you'll need to change the symbol table, and so on. Okay. So yeah, I definitely suggest using an association list. So it's just a good old cons style list where every element of the list is a pair, and then the car is the variable, and the cdr is the new variable. Okay. All right. Oh, and in Racket, there's this you can use. Whoops. Sorry, wide. You can use. There's these dict for dictionary, dict set, and dict. I want to say get. So there's this whole sort of dictionary library that essentially, do the lookup in the association list for you, or add to an association list. Okay. And then an empty association list is just an empty list, right? Okay. All right, I've got a question here. Does the compiler test code expect a specific type of structure for sim table? I think the answer to that question is no. The test code, I think, has no way of knowing what you're doing in terms of the symbol table, I believe. So that's sort of your own private business as to how you do that. Okay. All right, any other questions about Uniquify? If not, we will move on to remove complex opera star. All right, on to remove complex opera star. Oh, and actually, maybe before I dive into this one, just as an aside, a little compiler for a language like R1 sort of traditionally might have been implemented in just maybe 1, 2, or 3 passes, and not, here we are 5 or 6 passes. And what we're doing is we're following what's called a nano pass approach to compiler writing. And the idea is that every pass in the compiler is going to do just a very small amount of work, okay, and a very focused amount of work. So it has a very clear goal. It does that goal and doesn't worry about anything else, and just does one. So you're just doing one thing at a time. And the idea is to try to make these passes easier to implement and test by doing nano passes. Okay, so it's meant to be sort of an aid in terms of, from an educational standpoint. It does mean that your compiler may be a little bit slower because it has to make lots of passes over the program. But this actually doesn't matter that much, because each pass is an order n sort of operation for the most part, except for the register allocation pass is going to be n squared. And so that's going to sort of dominate like all the other passes. And so the rest of them aren't going to matter that much, and it's just register allocation that really matters. So, so yeah, this isn't absolutely super fast in terms of compile time, but you know, the idea is to have to do less debugging and to catch our errors early. Okay, so that's sort of some of the rationale for why we're doing NanoPass. Okay, so let's look at an example with remove complex opera star. So we've got plus 42, 10, and then maybe negative 10 here. Okay. So here we've got some operations that have complex subexpressions. Okay. So so well, maybe one thing to look at, kind of working inside out, this inner plus here is okay. It has its arguments 42 and 10 are both atomic. So I'll put a little check mark. That expression is just fine the way it is. And looking at this negation, its subexpression is a 10, that's atomic. So that one's just fine as well. Okay. So it's really just this outer plus that's problematic. In fact, it has sort of two problems. This subexpression and this subexpression, both of those are non-atomic. Okay, they're complicated. Okay, so we're going to have to introduce some let bindings for that. Okay. So what we're going to do is we're going to replace that plus expression with some let bindings. So here's a temporary variable, temp1, gets the first argument to plus. And then we're going to do another temporary variable for the second argument expression, which is negative 10. And then we're going to go ahead and do our plus operator. And then now we need to use the temporary variables instead of those complex subexpressions. So we'll have temp1 and temp2. Okay. And just to be really sort of clear about what this pass is supposed to do, I'm going to give you an actual grammar for what the output should look like. So this is for the R1 double prime language. So an atom is a variable. This is the concrete syntax, by the way, or an integer. And then an expression is an atom, or like a read, or a negation. But now it's an atom inside instead of just an arbitrary subexpression. Similarly for plus, 2 atoms, and then let stays the same. Let, you can have a variable and an arbitrary expression, and then still have an arbitrary expression in the body. Okay. Okay, so the main point there is that we've restricted these spots where you have subexpressions in the operators, and those now have to be atomic instead of being arbitrary expressions. In a second, I'm going to give a little bit of advice about how to structure your functions for this. But maybe any questions so far about like the problem statement of what this pass is supposed to do? We're good. Thumbs up. All right. Okay, so a little bit of advice about how to structure this. Actually, maybe before I do that, there's maybe one more sort of thing along the lines of the problem statement here. Okay, let's say we have a little program that doesn't have any complex sub-expressions in it. What do you think the output of remove complex opera star should be for this program?
It shouldn't change anything, should it?
That's right, Zach. It should be exactly the same. Right. Now, if you're not careful about how you write your pass, you might accidentally do the following instead. You might produce the following. Okay. You might, like your compiler might, whenever it sees an expression, it might go ahead and generate a temporary variable no matter what. Okay. And then you'll end up with something that looks like this. You'll end up with a ton of temporary variables that aren't necessary. Okay. So we don't want that. And so I guess maybe the question then is, well, how on earth do we avoid producing, that bloated version of the program with lots of temporaries generated where we don't need them, while also doing structural recursion? Okay, so we want to do structural recursion, but we don't want to generate unnecessary temporaries.
We kind of have a case guard or something for the recursion, for the structure part.
Possibly. Maybe one thing to think about too is that let's look at the grammar. So oftentimes it's good to look at grammars when you're thinking about how to structure your recursion. And one thing to notice, think about where we're going to do the recursion, okay? So we're going to do recursion where we see expression, right? So we're going to do recursion here on those red spots. We'll make recursive calls. And then also on the blue spots, we're going to do recursive calls as well, okay? But we kind of want to do different things for the red and different things for the blue, right? So for the red, those red spots don't need to be atomic, do they? They can just sort of be arbitrary expressions. Whereas the blue spots need to be atomic, okay? So one way to do this is to have two different functions that are actually mutually recursive, okay? Or, well, maybe not necessarily mutually recursive, but I forget actually whether they both call each other, but we'll have two different versions of the remove complex opera star. One version that says, oh, I want to process this expression and I need to turn it into an atomic expression. And the other one says, oh, I need to process an expression and it's okay to get a complex expression out. I don't care. Okay, and then we'll just use these two different functions when we're, invoking, the different sub expressions. Okay, depending on what we need for the output. Okay. So what do these two functions look like? I recommend calling them something like RCO atom. And the idea here is this one takes an expression as its first parameter, and then it produces an atom and a list of temporaries with what they're bound to. Okay, so this is going to be, you're going to have a variable and an expression list. Okay, so here we are, a list of variables paired up with expressions. Okay. And then the RCO, the other one, exp, takes an arbitrary expression and then just produces an arbitrary expression. Okay. So maybe let's just think about like what we would do in a certain case of the compiler. So let's say we're looking at a plus operator with two sub-expressions, E1 and E2. We need that E1 and that E2 to become atomic. So we're going to do an RCO atom on E1 and also on E2. And that's going to produce, we're going to have atom 1, and then we're also going to have the variable, sort of the temporary variables that got generated while processing E1. So I'll just call that VS1, okay? The temporary variables and the expressions they're bound to. And then for E2, oh wait, and you know what I didn't tell you? I didn't tell you which function we're currently processing in. Let's say we're in RCO atom, processing a plus operator, okay? So then the second one, we get back an atom, let's call it A2, and we get a list of variable bindings, VS2, okay? And then what do we need to do next? What do we actually need to return from, this RCO atom call on plus with E1 and E2? Okay, we need to return two things. We need to return an atom and a list of variable bindings. So what should the atom be? We've only got two choices for atoms. Atoms can be integers or variables. maybe let's scan back here a second. So let's consider this exact example, right? So we've done our recursive call, and we've got back our A1 and our A2 from processing, the plus 4210. And we've got back our list VS1 and VS2. I think in this example, those lists would be empty, but if you had a bigger expression, they might actually have some stuff in it. And so now we need to generate something for this plus, but we're in a context where we need it to be atomic, right? So maybe there's another plus outside of here. And so this inner plus needs to be atomic. So how are we?
Could we just call like A3 and then it has the value of plus A1, A2?
Sorry, say that again a little bit louder.
So if we want it to be atomic, do we just give it another variable name? So like A3?
Okay, so we need to generate a new temporary variable name, right?
Mm-hmm.
Yeah, so we can do like gensim, maybe temp. That produces, you can bind that to like A3 if you want, or whatever, right? So we're gonna return A3, right? So good, we're returning a variable. And then now we also need to return a list of variable to expression mappings, okay? And we need to be, and it's important that we preserve the semantics, right, of this program, right? So when we evaluate this variable, it better give us the same answer that we got when we did that plus, okay? And how on earth are we gonna make sure that that happens? And the answer has something to do with what do we stick in this list of variable to expression bindings. And maybe one other thing I should say is that this list of variable bindings, those are going to move up and they're going to turn into let bindings in a outer scope of what we're currently looking at.
So we add the plus A1 and A2 to the variable list.
Mm-hmm. And what do we need to do with A1 and A2?
So we need the value of A3. So we add plus A1 and A2 to the variable list.
Actually, here, let me. So we need to say, okay, A3, this A3 variable. Actually, I'm going to use a different name for it. I like to use X's and Y's for variables to just be very specific. Whereas A could mean I'm any atom, I could be a number or something. So X3, so we need to say, like, when we build the let binding for X3, what are we going to initialize X3 with? And the answer here is, well, we need to initialize it with this plus, right? And what are we going to do? We're going to add A1 and A2 together, okay? This dot here means I'm consing, I'm pairing up these, the thing on the left and the right of the dot, okay? And then I don't want to forget about all of these variable bindings from VS1 and VS2. For example, those probably have, like, let's say A1 might be a variable and its let binding is going to be coming from VS1, okay? So we need to put down, we have VS1, and then we're going to append all these things together, okay? And so we'll have a big list that, you know, starts with VS1 and then VS2. Actually, I don't think the order there matters. And then, but it does matter that at the end is where we put this new binding that says, okay, X, the temporary variable X3 is gonna get the value from adding A1 and A2. So we're gonna have this invariant that the atom that we return from RCO atom, well, it's either a variable or a number. If it's a number, it's just a number. If it's a variable, then the definition of the variable has to be over in the output list. Okay, and indeed, we're generating this new temporary variable X3, and we're adding an entry to that list for X3. And then there might be variables in here, and if there are, they're defined further out. You know, they're defined in VS1 or VS2. So already we're getting into a situation where the structural recursion is a little bit fancier here. Okay, we've got this situation where instead of having just one function, one recursive function, we have two. Okay, and this kind of pattern shows up whenever you need to do some kind of context-dependent sort of logic in your compiler. Okay, here we're dependent on whether we're in an atomic position, or whether we want an atom, or whether we want an expression. In the next pass, we're gonna use this trick again in a slightly different way. Okay. Oh, and also this trick of using two functions, it's equivalent to another approach where we just use one function, but add like a Boolean flag as an extra parameter to say, you know, true or false, do you want an atom or you don't care? Okay. That would be a totally equivalent way of implementing this. And then you'd have a big if condition inside of your recursive function branching on whether you want to generate an atom or an expression. Okay. All right, are we ready for the next pass, explicate control? Thumbs up, or any questions? All right. Okay. This pass used to be called expose basic block, and it was sort of infamous for being difficult. I think we nicknamed it was EBB, expose basic, yeah, EBB. We're always talking about EBB. This time with explicate control, this version of it, it's going to be a little bit easier than the good old version of it because we're doing the incremental thing. We're only dealing with the language R1 right now. This pass will get a lot more complicated when we get to a language with conditionals, with if expressions, okay? But for now, it's fairly straightforward, okay? So let's look at a little example here. Okay. All right, so here we have an R1 program. And again, from a control flow perspective, it's this, you know, depth first search, you know, figuring out what's going to happen. And so maybe I'll go ahead and what's going to happen? Well, okay, we're at this outer let. We're going to go into its the binding and the right-hand side of that. And we've got another let. So we go to the binding, the right-hand side of that. So this, I'm going to put a little 1 here. This negative 42 is the first thing that's going to happen, right? And then the second thing is that's going to happen is this, we're going to look up variable y, and that's going to go into, x. And then sort of like the third thing that's going to happen is we're finally going to get to the negative x down here. Okay. So that's sort of the order of the sequence of events. Okay, so what we're going to do, so we're going to convert this into a C0 program. Okay, so we're in R1 up here. We're going to go into C0. And we're going to have this convention that C0 programs always start with a label called start. And so the first thing that's going to happen is that we're going to do the negative 42 and put it in y. So we're going to have this assignment statement, y equals negative 42. And then the second thing that's going to happen is we're going to assign to x gets y. And then the last thing is the negative x, and that's going to be the return value of the whole program. Okay. So that's what the C0 program is. Now, with the C0 program, we also need to, we have these variables x and y. Where do they come from? Right? Why are we allowed to, use these variables x and y? Well, these variables x and y are essentially variables local to the main program, okay? And so we want to have a way of sort of listing out the local variables, okay? So we're going to have a list of the locals x and y, okay? And this part here, if you remember, there's this info field in the program AST node, and that's where we're gonna put these locals information. Okay, and that'll be handy later on when we need to do like assign homes. We'll have a list of, oh, here's the variables that we need to assign homes to. Okay, and so now we have this very, the order of evaluation is just sequential. It's just going to go straight down like that. And it's going to, 1, 2, and 3. Okay, so now we've made the control flow explicit. And we've really just flattened, for this language, it's just flattening the let expressions. Okay. Any questions so far about explicate control? Okay. Now I want to get into a little bit more of the nitty-gritty of how this pass is implemented. Let's go ahead and remind ourselves of the grammar for C0. Okay, so C0 has atoms, which is an integer or a variable. This is the concrete syntax. Has expressions, which are atoms, read, negative atom, plus atom. Okay, and then now it has statements, for now, it just has an assignment statement, which has a variable, an equal sign, an expression, a semicolon. That's for the concrete syntax. And then what we're going to do is we're going to make sure that, I mean, you could just say that a program, a C0 program is a list of statements, okay? But we want to be a little bit more precise than that because we want to make sure that it ends with a return, okay? And we're going to bake that into the syntax. So we're going to have this other non-terminal called tail that is either a return or it's a statement followed by a tail, okay? And so because the base case for tail is always return, you have to have a return. It's going to have to be at the end, okay? Because we put that over there. Okay, so you can have a number of assignment statements and then a return at the end is what we're doing here. And then the C0 overall is going to be like the start label and then a tail. And that's it. Okay. Now, the reason why I'm using the word tail here is that something in tail position means it's sort of directly in line for being sort of the last thing that you do in this function, okay? And I want to, there's going to be also a notion of tail position for the R1 language, okay? And in general, we're going to have this thing where like things that are tail in R1 turn into tails, things in tail position in C0. Okay, so let's sort of redo the grammar for R1, but with, we're going to take what's normally just an expression non-terminal. We're going to take this expression non-terminal and we're going to turn it into two different non-terminals, one called tail, but this is tail for R1, and the other one, let's call it, let's say NT for not tail, okay? And so now, like what we'll do is an R1 program is just one of these R1 tail things. And then a tail, oops, is, you know, essentially just an expression. So we're gonna have all the normal kinds of expressions. You know, negative atom. But then when we get to a let, there's sort of something interesting that happens here. So the body of the let is still a tail position, but the right-hand side here is not tail, okay? So it sort of flips over to being not in tail position, okay? Whereas, and then there'll be another, you've got the grammar for things that are not in tail position. And again, you have sort of all the usual expressions, but the interesting one is the let, where if you have a variable here, well, that's still going to be not tail position, but then the body of this let is also not tail because the whole let was not in tail position either. Okay. Okay. The reason why I sort of went through this, you know, this exercise of separating out tail and not tail is that for explicate control, we're going to want to, again, have two functions, okay? But this time, we're going to want to use, there's going to be two functions, one for when the expression, the incoming expression that we're processing is in tail position, and then we're going to have another one for when you're not in tail position, okay? And in particular, when you're not in tail position, where are you? It really means that you're here on the right-hand side of a let binding, okay? So in some sense, you're in what's going to become an assignment, okay, at the C0 level, okay? So the way I would recommend structuring your compiler is with these two recursive functions, one called explicate tail, and the other one called explicate assign. Okay. So this one takes an expression in tail position. And then it's going to produce, right? That's in R1. And then it's going to produce a tail in, that's in C0. And then also, we need to collect up all the variables, all the let-bound variables, because they're going to become local variables. So we're going to return a list of variables, so a var list. Okay, and then explicate assign, this one's a little bit more complicated. Okay, this one takes an expression, and this is, the right-hand side of a let, right, which is not in tail position, okay? It's going to take a variable, which is the variable from the let, and it's going to become the variable that you need to assign into, okay? And then we have yet another parameter that's a tail, okay? So this is going to be a C0 tail, and that's going to be the result of processing the body of the let. After recursion. Okay. So those are the inputs to the assignment, and then the output will be a tail and a var list. Okay, and this is again a C0 tail. And one way to think about this is that the job of explicate assign is essentially to generate an assignment statement that assigns, the result of translating this expression into the variable, okay, the variable that's coming. And then it needs to lay down sort of, after it lays down that assignment statement, it's going to lay down the rest of the program, or the rest of the body of the let, and that's going to be this tail part here. So you can think of that as sort of like the continuation of the program, okay? Okay. Any questions so far about these two functions? Okay, I think I'm going to use the last 10 minutes of class to do kind of an in-depth example, because this one's relatively subtle, okay? So let's go ahead and do this example. Let's see, can I fit it on here? I think I better start with a new. Okay, so we're going to do explicate tail. I'm going to abbreviate it like that. And we're going to use the same program So when we're doing explicate tail, so now we've got a let binding to deal with. The first thing we're going to do is we need to process the body of the let. Okay, this may seem a little bit counterintuitive, but we're going to go ahead and process the body. That's the negative. In this case, it's that negative x, right? So we're dealing with this let. This whole thing is the right-hand side of the let. This is the right-hand side, and this is the body. So we're going to process the body and the body is again in tail position, right? According to that grammar that we created for R0. So we're going to call explicate tail on negative x, okay? And then what that's going to do, that's going to produce return negative x as a statement, and then an empty list of variables, okay? Because there were no let bindings in the negative x expression, okay? Okay, so now we pop back up from that, and now we need to process the right-hand side, but this time, you know, it's a right-hand side, it's not in tail position, so we're going to use the other explicate function, the explicate assign, okay? And we're going to pass in that let y and so on and so forth. And then the variable that we're going to be assigning to is x, right? That's the variable for this let binding this let expression that we're currently working on. And then the third parameter to assign is, you know, the result of processing the body, which is going to be this return minus x. Okay. So that's the input to our recursive call where we're processing the right-hand side. Okay, so now we have to process the right-hand side. Again, we're going to process now the body of that. So we're going to do explicate assign the body y. And when we're processing the body, this is kind of funky, but we're going to use the body of a let inside of an explicate assign. The result of that body is going to get assigned to the same variable x, okay? And then the third parameter is going to be, you know, the result is going to be the same as what we've got passed in, okay? And then now we've hit a base case, we just have a variable here that we're dealing with. So we're now going to generate an assignment statement. We're going to assign y to x. And then we're going to take the rest of that stuff and lay it down afterwards. Okay. And that worked out nicely. We've got the assignment to x coming before we actually negate x. Okay. So that finishes processing the body of this right-hand side. So we processed that y. Now we need to pop back up and process the negative 42. So we're popping back up. We've got another explicate assign. Keeping track of the recursion here, you'll notice I'm indenting to try to help me keep track of that. It's a little bit mind-bending. So we're processing negative 42. That is going to get assigned to y, right? So we have y there. And then what comes next is, you know, the result of processing the body, which is all of this stuff. So x equals y, return minus x. Okay. With 42 or negative 42, that's actually, you can treat that as a base case. So we're going to generate an assignment statement. Y gets negative 42. And then we're just going to lay down the rest of what came in here. So we have x equals y, and then return x. Okay, so that finishes that. Now popping back up, we're back up to here for this explicate assign. And we've got most of our work done. We basically just need to go ahead and the result here from that inner one, we're gonna go ahead and put that down. So we're gonna return that. Oh, I should have mentioned that in each of these results here, we're returning the list of let-bound variables that we dealt with. Oops, which I've forgotten to deal with. I think from here we would have, where did the x? Oh, actually, we haven't hit we're not where we need to be for the x yet. We basically just need to return, since we're currently processing this let y, we need to go ahead and say, hey, y is a variable, okay, that needs to become a local variable, okay? And then once we're finished with that, we're gonna pop back up, all the way back up to here where we're processing the let x, okay? And again, the result just propagates to there, but now we need to add x to the list of variables. So we're gonna have x and y there. And at that point, it's a simple matter of generating a program node where your info has the locals mapped to this list, and the body of your program has this sequence of statements. Okay. All right, good. We made it through that example. All right, we've just got a couple minutes left. Any questions about this little dance that we did? If you're feeling a little bit blown away or confused, that's okay. Sometimes it just takes multiple exposures to an idea to have it sink in. So now you've had one exposure, and you can, I'd recommend maybe reading the textbook, reading this chapter over, and maybe spending a little bit of time on this particular pass, thinking about how it's working. Maybe try to work through by hand a little example could be helpful. And then you'll start trying to code it up. And it's sort of like a little puzzle, and you can kind of think about like, okay, this is given what's coming in, what's going out, how can I satisfy these constraints? And then there's, you can look at these examples. Where was that? Yeah, so you can do an example like this. You can come up with your own examples. Once you have the code, you can start, running the code through and seeing if it comes out the way you expect, and if not, back to the drawing board and stuff like that. And I will be available for office hours, so please don't hesitate to take me up on that. You've paid your tuition, and as part of that, you get various benefits like office hours with me and with Jenner. So make good use of your money. We're happy to talk with you and help you work through some of these trickier parts. So my alarm is now going off, so it's time to finish up. Last questions?
I have a question real quick.
Yeah.
My apartment maintenance showed up in the middle of this lecture. Will this be posted online soon after class?
Yeah. So what I've been doing is this is recorded, and it's using the it's Zoom, and then it's using the Kaltura thing, and so it a little bit depends on how fast Kaltura does its thing. But sometime later today, I'll probably get an email where Kaltura has said, "Hey, I've finished processing your video," and as soon as I get that email, I'll go ahead and put a link to it. So it might be later tonight by the time that happens, but it definitely will be available.
Okay, cool. Thank you.
Great. All right. Well, with that, I'm off to a cross-country meet. My daughter is going to be running in the junior high cross-country. It'll be fun to see. All right. Take care. Stay safe.